Hello, and welcome to the second part of section 10.4, Empirical and Molecular Formulas. Today what we're going to look at is we're only going to look at how to find an empirical formula, and then in the part 3 video we'll look at molecular formulas, and that will come later in the week. So before we can figure out how to find an empirical formula, we kind of have to know what it is. So an empirical formula is just the formula unit with the smallest whole number mole ratio of the elements. Okay, it could or it could not be the same as the actual molecular formula, which we'll look at in the part 3 video. So if we look at the example of peroxide, peroxide is actually H2O2. So this is peroxide's molecular formula. This is the exact formula or recipe that you would have to make peroxide. However, if we're looking at just the empirical formula, both this 2 and this 2 are divisible by the same number, which is 2 in this case. So we could reduce the ratios and just write this as hydrogen and oxygen. So this here is the empirical formula, while this here is the molecular formula. So in order to find the empirical formula, what we have to do is we have to look at the percent compositions of masses in the elements, which is what we did in the first video. And we can use these to help us find the formula for the compound. So what we're going to do is we're going to have to convert our mass to moles. Then we're going to convert any non-whole number ratios to a whole number ratio. Okay, and usually we'll do this with division. Okay, and I'll show you how to do this here in just a second. And then every now and then, because things might not work out to a nice whole number, we might have to multiply by some factor to give us a whole number. So let's go ahead and look at our first example. Example 16 says that methyl acetate is a solvent commonly used in some paints, inks, and adhesives. We're going to determine the empirical formula for methyl acetate with the following chemical analysis. We're told that we have 48.68% carbon, 8.16% hydrogen, and 43.2% oxygen. So because we are dealing with a percentage basis, remember that a percent is always based off from 100, okay? So if I have 100%, I can easily convert this over and say that we're going to assume that each percent is a gram. So this tells me then that I'm starting out with 100 grams, okay? And this is just going to make our computation a little bit nicer. So with that being said, I'm going to start out with the 48.68, and even though it's a percentage, I'm going to assume my percentage is a gram of carbon, and I'm going to convert that over to moles. And I'm going to do that by multiplying by 1 mole of carbon for every 12.01 grams of carbon, and that just came from my periodic table. And if I multiply and divide that out, I get 4.050 moles of carbon. I'll do the same thing with hydrogen. So 8.16% becomes 8.16 grams of hydrogen. And again, I'm going to multiply that by 1 mole for every 1.008 grams that I get off the periodic table. And this is going to give me 8.10 moles of hydrogen. And then I'm going to do the exact same thing with my oxygen. And oxygen is 43.2%, or in this case, 43.2 grams. And I'm going to convert that by going 1 mole for every 16 grams, and this will give me 2.7 moles of oxygen. Now what I'm going to do is I need to set up a molar ratio. So to do that, I'm going to go and look and see which value is the smallest. So I have 4.050, 8.1, and 2.7. Because the 2.7 is my smallest number, I'm going to then go and divide each one of these by 2.7. And that what that's going to do is that means that one of my ratios is going to have to be 1. So 2.7. And when I do that, let me slide this over. Oh, that's not going to work, is it? Okay, so when I simplify that, that is going to give me 4.05 divided by 2 is 1.5. That's moles of carbon. 8.10 divided by 2.7 is roughly 3 moles of hydrogen. And 2.7 divided by 2.7 is going to give me 1 mole of oxygen. So let me just write this on a clean sheet of paper and we'll continue the problem here. Okay, so if I clean up the last page, since it wasn't letting me slide the whole thing around and keeping everything intact, essentially we had 1.5 moles of carbon, 3 moles of hydrogen, and 1 mole of oxygen. Well, by definition of an empirical formula, we have to have the lowest whole number ratios. So by looking at this, we can see that carbon is not a whole number. But if I multiply it by something, I can get it to a whole number. So if I go and I multiply everything, because I can't just do it to one thing, by the number 2, so if I multiply this by 2, I end up with 3 moles of carbon. And I multiply this by 2, I end up with 6 moles of hydrogen. And I multiply the oxygen by 2, this gives me 2 moles of oxygen. I now have whole number ratios, and if I go and I write my formula now, I have C3H6O2. And this here is going to be my empirical formula. And we will do one more example just to make sure it all makes sense. So our last example says to determine the empirical formula for a compound with the following chemical analysis. It tells us that we have 81.79% carbon, 6.1% hydrogen, and 12.11% oxygen. Again, because we're given percentages, we are going to assume that each of these are in grams. So that tells me that I have 81.79 grams of carbon. We're going to multiply this by 1 mole for every 12.01 grams of carbon, and we'll get, this gives me 6.81 moles of carbon. Then I'm going to do the same thing for hydrogen, so 6.1% is 6.1 grams of hydrogen, and we'll multiply this by 1 mole for every 1.008 grams. And with that, I'll get 6.05 moles of hydrogen. And then finally, I have my oxygen, which is 12.011 grams of oxygen. And I'll multiply that by 1 mole for every 16 grams. And when I divide that out, I get 0.75 moles of oxygen. So again, I'm going to go through and I'm going to divide all of these out by the smallest number. And by looking at my 3 values, I see that 0.75 is the smallest. So if I go through and divide all of these by 0.75, I know that this is going to give me 1 mole of oxygen. On my calculator, I get 8.0, and then it's 6 repeating, but 8.06 is pretty close to 8. So I'm going to say this is moles of hydrogen. And then if I divide 6.8 by 0.75, I end up with, this is going to give me 9.08, but again, I'm just going to leave that at 9.0 moles of carbon. So in this case, I got numbers that are pretty close to whole number ratios. So what I'm going to do then is I can just use these and write my formula. And that formula then is going to be C9H8 O, and then you can put the 1 if you want, or you can just leave it. So C9H8O is my empirical formula for this chemical analysis. Please let me know if you have any questions. Otherwise, have a great day.